So I left you with this exercise. So the key thing here is to look at the conversion that we need to do between cos squared and to turn it into a simple cosine, not a squared cosine, that we can actually start to draw. So if we look at the example here, we need to remember this trigonometric identity up here, and you can go through the steps of it here, but essentially what we have to remember is that we're going to get a 1 plus outside. So we had 6 in front of the cos, so we're going to get that outside. We need to take this, remember to take this 2 into account, so we'll get 6 on 2 plus, or 1 plus, and that all goes inside. And then we need to double everything that is inside the brackets. So the important thing to remember here is we double both the frequency, so 2 pi instead of 32 we now get to 64t, plus we also have to double the phase shift, so we get 2 pi by 4, which is equal to pi by 2. So we've doubled both the frequency and we've doubled the phase shift. The other thing, when we draw it, what we have to note is we've got this 1 plus at the front here. And so, as we show at the bottom here, we end up with 3 plus 3, 2 pi 64t plus pi by 2. I said I've forgotten to write cos in here. There we go, cos. Now, we have our frequency of 64, we know how to draw that. We've got our phase shift of pi by 2, we know how to draw that. But what do we do with this plus 3 out the front? Well, what is a constant? What is something that doesn't change with frequency? It's a DC offset. And so if you looked at every value, this 3 cos term here is now going to go between plus and minus 3. So at the height it will be plus 3, at the bottom it will be plus minus 3. So if we add 3 to it, this 3 plus is now going to go between 0 and plus 6, because we always add 3 onto it. And so what we see is that we actually just have a DC pedestal, a DC shift of a value of 3. So our sinusoid now starts at 3, goes down to 0, then goes up to plus 6, back down to 0, up to plus 6 again. And so we have our shift is now between 0 and 6. And if we were going to draw this out on a frequency diagram, we have our frequency of 64 and our amplitude of 3. We have our frequency of 64 and our shift of pi by 2. And we also need to draw our DC component. Well, our DC component doesn't have a frequency, so essentially it has a frequency of 0, so we draw it here. It doesn't really make much sense to ask what the phase of a DC component is. It doesn't shift, so it has no phase. So we don't really need to draw anything on the phase spectrum. And so we would draw out our frequency spectrum. Again, this should be in hertz, something like that. So we can now look at another way of representing our sinusoid. We can represent it as a vector. And to do this, we need to remember our vector space, essentially the space we talk about when we talk about the complex plane. So here we're talking about a vector that might be in the real plane or that is in the imaginary. And in most cases what we're talking about is something that has a component both in the real and imaginary plane. And so maybe some point on this plane that has both a real component and an imaginary component. So what does this look like for a sinusoid? Well, if we think about a sinusoid as a vector, and we look at what it means in the real and imaginary, essentially what a sinusoid is a rotating vector. So it's a vector that has a length of v0, so that's our amplitude. So if we define our sinusoid as v0, sine or cos, you should probably do this against cos, then we will get v0 cos omega 0 t plus phi 0. So we have our 3 components here. We have our amplitude, which is the length of our vector. we have our speed, which is going to be determined by omega naught t, that's how fast it rotates, and we have our initial starting point. So if this was 0, then we would start on the real axis. If it was plus pi by 2, we would start on this imaginary axis, and so on and so forth. So we have length, speed, and phase. So what does this mean? Well, it means we can plot what's going to happen as our vector spins. And what we see is that our sine function is going to be the angle that the angle that this makes to the imaginary function, and our cosine is going to be the line that it draws against the real axis of our complex plane. So as we start to rotate this vector, you can see on the sine we're about to reach a peak, whereas on the cosine we're about to reach 0. And we're in 0, and we're going to move round, and we're going to move round until we get right the way back round. And so here, when our sine is at our 0 point, our cosine is at our, when our sine is at our minimum point, our cosine is going to be at our 0 point, and so on and so forth. So that's thinking about the sinusoid as a vector. But there's a bit of a fix here. When we think of it as a vector, what we're actually saying is we want to see it against the imaginary axis or against the real axis. And so we're actually saying our real value is going to be the real part of that rotating vector. Now we can do that using a complex, we can describe our vector using our complex representation, because we know our vector has a real component, what it makes to the real axis, and a complex component, the line it makes to the imaginary axis. Now, using Euler's equation here, we can actually write out our cosine part and our sine part, which was the two parts we showed in that previous diagram. Now, taking these two things together, this identity here and the two parts, we know we can write that vector that spins as this complex form here. So we have v naught, our length, e to the j, omega naught, which is our frequency, phi naught, which is our phase. So this gives us an equation for that vector that is spinning. But as we said, our real cosine, the cosine that we usually use in our signal representation, was actually a real function. When we looked at the vector, and our vector was here, what we were interested in was the line it makes on the real axis to give us our cosine. Now our complex form, this that we have here, gives us this whole vector in complex space. So to find the real part, there are a number of things we could do. One thing, we could use this like mathematical trick here and say, actually, I just want the real part of this. So take the real part of this complex exponential. And of course, we said here, the complex exponential is this real part here plus this imaginary part. So if we get rid of the imaginary part, we're just left with v naught cos omega naught t plus phi naught, which is what we were after as our real cosine. But that's a bit messy. That's not quite how we want to do it. We don't want to have to start taking the real part. But there are other ways of doing it, which we'll come back to in a minute. But before that, let me give you one more exercise to do. What I'd like you to do is use either the complex exponential form that we've just talked about, and to write down in complex terms what these three equations of signals actually look like.